So thank you for being back. Now we'll take the next speaker. We are very happy to have Jonathan Rodenfels, who is coming from the Max Planck Institute CBG in Dresden. And thank you, Jonathan, to be with us. We'll look forward to hearing about energetics in biological systems.
Great. Thank you, Thomas. And thank you for the invitation. It was a little bit of a struggle getting here yesterday, but I finally made it. I slept about 4 hours, and I'm going to talk about something I've never talked about. So just give me a little bit of a break today. But generally, my lab, or our lab, is interested in how flows of energy and matter, as well as cellular metabolism, shape the behavior of out-of-equilibrium systems, for example, developing embryos or cells. And I want to principally just start my talk while sharing a little bit of trivia, where we're just going to compare who is more powerful on a per kilogram basis, and is it the sun or an average human being, right? So this morning you hopefully had breakfast, and like on the average, right? Like we need around 2,000 kilocalories per day in form of energy in the nutrients, right? And we can convert these units of 2,000 kilocalories per day in joules, and then have a look, convert the days into seconds, and that you arrive roughly as an energy expenditure of an average human being of around 100 watts, so 100 joules per second, which we all dissipate to the environment in the form of heat, right? In the form of heat. And now post-corona times, we may be together in the room, and you realize after some time, oxygen gets depleted and the room heats up. And then if you normalize this now, just keep it simple, by an average weight of a human being of around 100 kilograms, that arrives you to a mass-specific heat dissipation to the environment of roughly about 1 watt per kilogram. Now you can go back and get data from the NASA and think about how much energy does actually the sun dissipate and how heavy the sun is. And if you do that calculations, you arrive at a mass-specific energy dissipation of the sun, which is 5 orders or like 4 orders of magnitude lower than the mass-specific metabolic rate of an average human being. And I find this unit, or like this little game, very, very interesting, because it tells you somehow that maintaining life is actually, on a per kilogram basis, quite expensive. Of course, the sun is so big and so much energy, and we all required the sun, which probably gave the energy which was required for the origin of life. And you can do this now with if you normalize this per an estimate of numbers of cells in our body, a single cell dissipates roughly about 100 picowatts, or 10 to the minus 12 watts. And why is that, right? Overall, why is, a fundamental feature of all living systems is that they are active open systems that, through continuous exchange of energy and matter with their environment, keep themselves away from thermodynamic equilibrium, right? We all heard eventually somehow in textbooks about the second law of thermodynamics, where we say the entropy of the universe always has to increase. Life is exactly the opposite. We are very ordered and structured, so we have to expend energy and dissipate entropy in form of heat to the environment to keep us with the second law of thermodynamics. And that reason is that even in the early days already, people have proposed that the free energy expenditure or the entropy production to the environment somehow constrained biology and biological functions. And I want to just share you like two works in the early 2000s. One is from Alfred Lotka. And Alfred Lotka is most famous for the Lotka and Volterra model about predator and prey. However, he already published two papers back-to-back in 1922, where he postulated that first principles of the laws of thermodynamics somehow constrained the evolution of life. And his works can be interpreted as the organism that captures the most energy from the environment and dissipates the least amount of energy to the environment will automatically prevail. The second work is by Ilya Prigogine, who won the Nobel Prize for linear thermodynamics, and he proposed that his work is applicable to biology And one way he can interpret is that, for example, when an organism develops, undergoes development, over the course of development, an organism may minimize its mass-specific dissipation to the environment. However, now, about 100 years later, I would still argue that we still don't understand the most basic questions about energy flows from a quantitative perspective. So, for example, how much energy does it actually cost to stay alive for an organism? How much more energy, for example, does a cell need to divide and double its mass? Or how much energy does an embryo need in order to develop? And similarly, if we can start to understand this, can we now start to ask questions whether energetics at all constrain biological systems? For example, what is the cost of growth? In the end, how robust can you develop? Do you have to spend energy for robustness? How fast you can develop? And so on and so forth. But then moving from the scale of cells and embryos down to the subcellular and molecular scale, what we also like to understand is, how is that energy and matter converted by your metabolic pathways in time and in space to drive all this beautiful active cell biology within cells? And then, of course, how is that energy and matter allocated to these active cellular processes? So in the lab, we're currently working on all of these scales. On the embryonic scales, what we're trying to understand is using a comparative approach to look at the developmental energetics of various species across the phylogeny. And we do that experimentally using a technique called colorimetry to measure the heat dissipated of these embryos with the environment. And then on the subcellular scale, we try to relate those overall features down to mitochondrial cell biology, and where and when do mitochondria provide energy for active cellular processes. But today, what I want to share you with a little bit, a work which I started 2 years ago with my collaborator at the Gulbenkian Institute in Lisbon, Pablo Sartori, and his postdoc Tommaso. And I wanted to talk a little bit about the thermodynamic constraints of unicellular life across evolution, and particularly about the cost of growth, the energetic cost of growth. And you can start asking a question, for example, how could thermodynamics constrain growth? Right? If we now assume, for example, your favorite bacteria, let's say it's an E. coli, it uses nutrients from the environment, for example, glucose, and aerobically respires glucose or oxidizes these glucose to CO2 and water. It has a nitrogen source and makes biomass over time. The first law of thermodynamics tells us that energy is conserved, right? Like there's no energy produced nor destroyed, it's just converted from these nutrients into biomass. And the second law of thermodynamics tells us that system is out of equilibrium, so we need to dissipate energy into the environment in order to increase the entropy of the universe. And when we talk about energy, we want to link this to cellular metabolism, right? And because cellular metabolism, by definition, are these chemical reactions which extract energy and matter from the environment and build all the building blocks which make up all life. And we all probably have seen this picture eventually during our classes, and it's very complicated. So how can we even start tackling understanding the energy flows through such a network? And on the one hand, there are two views of metabolism. On the one hand, you have something which is called flux balance analysis. What you're trying to do is you use a genome-wide metabolic network reconstruction of all the chemical reactions within your system, and you try to model the fluxes through every chemical reaction. On the one hand, that gives you hundreds of variables, hundreds of chemical reactions, even thousands, but you do need genetic information. How does this metabolic network look like? And you need chemical information of all the metabolites in your network. On the other hand, there's this classical engineering approach using an idea of chemical transformations or just looking at the input and output. Let's just ignore all the complexity of the cell, and let's just look at the input in form of nutrients coming in and the nutrients coming out. So what we can do is we can reduce this complexity down to 5 to 10 variables in form of the nutrients and It's basically one overall macrochemical reaction, and we only need chemical information of these variables. And if we do so, now let's just go back to our hypothetical system, and we're saying, let's just think about this division of these two cells as one chemical reaction. We can write, glucose plus oxygen plus a nitrogen source gives you biomass, CO2, and water. And this chemical reaction is characterized by a parameter set. On the one hand, the classical metabolic parameters we do know is, for example, how much oxygen is consumed, or if you have fermentative metabolism, how much fermentation products you produce, or how much ATP do you need used, or how much of a certain metabolite. But on the other hand, since it's just a postulated chemical reaction, we can also say this reaction has thermodynamic properties. On the one hand, like what is the free energy change, what is the enthalpy change, and what is the chemical entropy change of that reaction. So now, just to iterate our approach, let's just go back to the textbook and think about the thermodynamics of a chemical reaction. Right? Maybe this morning we had some eggs or boiled some water, and we burned methane to generate heat in order to heat up our skillet. And if we want to know how much energy do we get, we can write down a chemical reaction, a simple one like that, where we have methane burning with oxygen gives you CO2 and water. Now we learned, right, we can solve this stoichiometry because of element conservation. We know that the carbon coming in equals the carbon coming out, and now we can solve the stoichiometry of 1 mole of methane gives you 1 mole of CO2 and 2 moles of water. And now, if we want to know how much heat is released, we can calculate the enthalpy change of that chemical reaction by plugging in the enthalpies of formation of the products, and the sum of this minus the enthalpy of formation of the educts, and that gives you roughly about 900 kilojoules per mole of methane burned. Similarly, we can do the same thing for the chemical entropy change of that reaction, and overall that gives you the overall free energy change, which can also be calculated from the other two properties there. And that was for a chemical reaction. But now, let's assume a cell is also a chemical reaction, and we can write down the same thing. In the end, we have our substrates and we have our products. Think about the cell as a catalyst, and it makes biomass, which is conserved in the system. Now we can write down the same element balance, all the elements coming in minus the elements coming out minus the elements conserved in biomass equals 0. We can write the thing for the enthalpy change, or the exchanged enthalpy. It's the enthalpy of formation contained in the substrates minus the enthalpy information of the products. And that equals the heat, or the law of Hess tells us that it equals the heat dissipation if we consider how much heat or how much enthalpy is conserved in biomass. And this gamma is the growth rate. We can do this for the chemical entropy change as well. And then we can write down the second law of thermodynamics, saying that you always have to produce entropy, which is the heat, the chemical entropy exchanged, and the entropy conserved in the system, and that must be larger than 0. And with the definition of the chemical potential, we can write down the second law in forms of the free energy change of the whole system, saying all the free energy change, free energy coming in minus the free energy coming out minus the energy conserved in biomass. Okay, so now we treat just growth as a chemical reaction, and what we can do now is just to go to 8 decades of literature of growth data and just go into the growth data and think about, collect them, growth rate, yield coefficient, so how much biomass do you make per gram of substrate consumed, and we can write down, based on this growth data in minimal media, we can write down a chemical equation describing this growth process. We then can use the measured stoichiometry coefficient, so yield, and use element conservation to compute all the other yields of that chemical reaction. And then we can go to a chemistry database and find the chemical potentials of all the molecules involved in this reaction. And we have done this and repeated this around 400 times. And now we can calculate the thermodynamics of unicellular growth for all these these processes, and then we can start answering questions or investigate questions about the thermodynamics of growth. But of course, it's very arbitrary, right? Like eventually you want to validate your approach, and one validation is we haven't imposed the constraints of the second law, but if we look in our data, all basically except two obey the second law, so they produce entropy and the overall free energy change is negative of growth. The second approach is when we had more yields and we could validate the element conservation for about 100 data points, we can look at whether we miss any elements in our chemical reaction. And if we do that, most of them have a relative error in the element conservation, which is roughly around 0. There's one outlier up here. And the third validation is the law of Hess. I told you that the enthalpy change of this whole chemical reaction should equal the heat dissipated. And heat dissipation can be measured using a technique called colorimetry, and the first colorimeter was actually developed by Lavoisier and Laplace in the late 1800s, where the chamber, the experimental chamber, is surrounded by a thin sheet of ice, and whatever you put in there, if it produces heat, it melts the ice, and the volume of the melted ice is proportional to the heat dissipated. And even at that time, Lavoisier and Laplace put a guinea pig in a calorimeter, and they also measured oxygen consumption and CO2 production. And what they concluded is that respiration, or our respiration, is in fact a chemical combustion reaction. I find this amazing at the time. Of course, now in our data set, we had about 100 data points with quantitative heat dissipation measurements. And what you can do now is you can compare the measured heat dissipation to the predicted one from our approach. And as you can see here on this log-log plot, is that the predicted enthalpy change really, really well matches the measured heat dissipation of all these data points. And I find this amazing that we can reduce the overall complexity of these massive metabolic networks down to a single chemical reaction, and we can predict a heat dissipation which actually measures the measured one. Okay, so now we can go and look at our data, right? We have around 400 data points, and it samples roughly all domains of life, from archaea to prokaryotes to eukaryotes. It has all kinds of trophism, autotroph, heterotrophs, autotroph fixing carbons. Litotrophs, we have aerobic and anaerobic respiration in there, fermentation, methanogenesis, denitrification, nitrification. And we can now look at this diversity of microbial or unicellular life in terms of its thermodynamics. And what we do is, on the one hand, we use the yield as a parameter. So the yield is how much biomass you get per electron donor or substrate consumed. The other one is the dissipation. So how much energy do you dissipate to the environment, normalized by amount of electron donor consumed. And we look actually at the cost, or the cost of growth, which is the dissipation divided by the yield. So how much energy do you dissipate to the environment per carbon mole of biomass grown? And if we start looking at the yield, what you can see is that the yield is very variable across all these unicellular life. And the most yieldful ones are aerobic respiration of disaccharides up here, and the lowest yieldful ones are actually hydrogenetropic methanogenesis. And similarly, what you can see is for the dissipation is that it's similarly variable, and again, hydrogenetropic methanogenesis is the least dissipative, and the most dissipative is aerobic respiration.
So this is different organisms?
This is all different organisms. It's grouped by electron acceptors, so whether you transfer your electrons through oxygen, or whether you do fermentation, right? We have an internal electron acceptor, or you use some metals, like iron, or whether CO2 gets fixed and it accepts electron acceptors. And the color code is actually the electron donor, whether it's hydrogen, acetate, or glucose, or glycerol. And that's all different organisms, and I'll come to this in a little bit. So they're highly variable, and of course, it's kind of like expected. We know that unicellular life is remarkably adaptable to physical chemical conditions in the environment. But to investigate the growth, I told you the cost of growth is the yield divided by dissipation. So we now plotted the yield against the dissipation, and what you can see is again that E. coli up here, prokaryote glucose respiration, is very yieldful but also very dissipative. but then the yeast, the eukaryote, is in a similar area doing glucose respiration. If we now look at fermentation, like not oxidizing completely the glucose, but you ferment it, for example, to acetate in E. coli or to ethanol in Cerevisia, they're in the middle of the pack, and again down here are the hydrogen-trophic methanogens. However, what you can see is that if we look at the cost as the dissipation divided by the yield, you can see that there is a feature that they seem to be linearly correlated in this log-log plot. And we can now look at, and there's some variations which I'm going to come to in a minute, but we can now plot the mean of each of these individual metabolic types, and then we can fit a linear equation to this data, which we leave, and the slope of this should be the cost, and that we arrive roughly about 600 kilojoules per carbon mole, which seems to be conserved irrespectively whether you're prokaryote, eukaryote, or an archaea, or what kind of metabolism you do. It seems to be universally conserved within certain amount of variability across life. Of course, there's some variability, and there's something interesting about whether you respire with oxygen or whether oxygen is around or not, and I will get to that hopefully in a few minutes. So now let's just put this cost which we get, this conserved cost, in perspective. Carbon mole is sometimes a very weird unit. So we can convert this, for example, in grams of bacteria, or like unicellular material grown, and you arrive roughly about 25 kilojoules per gram, or if you do it on a per cell base, that's about 7.5 nanojoules per cell. You can also do this in ATP equivalent, so you can use 40 kilojoules per mole of ATP hydrolysis, and then you roughly arrive about 4 times to the 10 to 11 molecules of ATP. If you now go back to the literature, what has been observed prior is what we determine is roughly an order of magnitude, a 10-fold higher to any estimates which have been made out there. And now you can ask, for example, what causes this conserved dissipative cost? On the one hand, you may say it's trivial, right? Biomass composition across the domains of life are very conserved, right? We have roughly a certain conserved amount of protein, lipid, and so on and so forth in our cells. And indeed, if we look at the contribution of the free energy change conserved in biomass to the overall contribution of the cost, that's it's very conserved across the domains of life in our data set. However, the contribution is very small here on this log scale, roughly 10%. So it's probably too small to contribute to this cost, and it's fundamentally different from the dissipative cost of growth. This cost is only the energy conserved in making your bonds in your biomass, but it does not account for all the metabolic pathways and irreversibility of energy dissipation leading to making, for example, ATP. Another way you can think of is this conserved amount of free energy maybe due to a conserved amount of free energy absorbed in your substrates or products. And if you now plot the substrate free energy variability in our data set against the cost, you can see is that the cost is conserved, but the substrate free energy variability is much larger. And similarly, we can look at this plot comparing the variability of the substrate free energy intake and the product free energy intake, and the variability is much larger than the variability of the cost. And I don't know what happened. All right. So we're left with a third one, which we don't fully understand, but maybe the variability in the free energies absorbed and released compensate each other to result in the conserved cost of growth across unicellular life. And indeed, if you plot the free energy produced in the form of substrates versus the free energy consumed, you can see this beautiful linear correlation across. So meaning that if you consume little free energy, you dissipate little free energy, giving rise to this conserved cost. And if you consume a lot of free energy, you give rise to, and you dissipate a lot of free energy as well. So this case tells you that, and then excuse the units, this is now in thermal energies, but the cost of making biomass or conserving energy in making your bonds is very little. The majority of the cost arises due to some feature which we don't fully understand of the metabolic network, making this energy conserved despite whatever orders of magnitude variability in the energy you consume. So in the last little bit, I want to talk a little bit about what else can we learn from this data, right? Like I only told you that the conserved cost, the dissipative cost is conserved, and it's roughly 600 kilojoules, but the way you allocate this energy can be different. The only way the second law of thermodynamics tells us is that we can either exchange this energy in the form of heat or in the form of entropy exchanged, or any combination of those two. So now we can plot these two together and look how do these different organisms obey the second law of thermodynamics. And we can see 4 little clusters. And the first cluster is entropy absorbing, right? Hydrogenotrophic methanogens, they consume 2 gases, as hydrogen and CO2, reducing the entropy of the environment, and they only produce 1 gas, which is methane. So somehow they compensate by an even larger dissipation of heat, as such that the overall dissipation becomes positive. Now, aerobic respiration, our classical respiratory metabolism, is heat-dominated. So most of our dissipation is heat, and the entropic contribution is neglectable. Fermentation, so producing ethanol or acetate, or in our case, lactate, is entropy and heat balanced, meaning that fermentative metabolism dissipates roughly the equal amount of heat as well as entropy. And then even then, there is acetoclastic methanogens, which are proposed or predicted to grow endothermically. So they take up heat via growth, and then they compensate by a larger entropic exchange with its environment. And this data has actually been measured, and acetoclastic methanogens, nobody wants to work with them because they're so hard to grow, but these guys actually take up heat when they grow. So what I've shown you so far is that what we can do with our minimal non-equilibrium thermodynamic approach is to look at the dissipative cost of growth, and that seems to be conserved across multicellular life, and it likely arises from a compensation and a free energy compensation across metabolisms. The second one is that metabolic rate from a thermodynamic perspective can be any combinations of heat and entropy produced, and that all these combinations are actually used by unicellular life. And then there's something interesting about oxygen, and maybe I used the last minute to go into this oxygen data. What I showed you is, of course, we have this conservation, but we also have this variability within metabolic modes. And this variability seems to be either invariant to the yield or negative with the yield in the dissipation. And we can plot this now for all the kind of metabolisms, and you can see is all these little round dots are actually oxygen using microorganisms, and they all have this negative trend in the relationship between dissipation and yield, and all the ones which don't have oxygen have an invariant dissipation. No, I don't want to shut down my computer. And we can also fit this data. So we were wondering, because oxygen was a very important transition in life, so we were wondering what happens now if we have the same organism on the same carbon source like glucose, but one has oxygen and one doesn't have oxygen. What happens? And we have 13 pairs of this data, and you can see that all of these pairs of data, they increase their yield as expected, and that has been known that aerobic metabolism is very yieldful. But similarly, these pairs in the transition from oxygen to non-oxygen also increase the dissipation. However, the cost stays constant. So, interestingly, but within this variation, they show this negative trend, which we call a cost correction, meaning that aerobically growing organisms can further increase their yield due to variability in physicochemical parameters or maybe the underlying metabolic network by actually increasing their yield by reducing dissipation. So they somehow become a bit more efficient, and we can now analytically solve this for a lot of different our data sets, and you can see these interesting outliers here. That's the nitrifying bacteria, which have been proposed maybe to be precursors to our mitochondria early on. So overall, what I'm showing you today is that in the absence of oxygen, there's some variability within your metabolic network where you can increase your yield, but you cannot reduce your dissipation. Think of that as a Lecuit current. However, if you further want to increase your yield, oxygen as an electron acceptor made you more yieldful, but you also incurred a higher dissipative cost due to this conserved cost. However, then within variability, aerobic respiration shows a trade-off between dissipation and yield, where you can further increase your yield by reducing dissipation, but overall, the cost is conserved. And with this, I would like to end. Thank you for your attention, and I'm happy to take questions.